Okay, so just to kind of review what I've said so far before we really get into the mathematics of the thing. Okay. First of all, a collision typically dissipates energy and or changes from kinetic to potential or potential to kinetic energy. Okay? And I guess this is an and or too. This means that kinetic energy is not conserved in a collision. Kinetic energy after collision can be very different than the kinetic energy before the collision. Now, if there's no change in potential energy, and there are no non-conservative forces, then the work kinetic energy theorem ensures that kinetic energy is conserved. Okay? Now, if energy is dissipated, it's dissipated by non-conservative forces. Okay? So anyway, if we have this situation, then we say the collision is perfectly elastic. Okay? If the objects merge, for example, a bullet into a block of wood, okay? Two vehicles collide and stick together. This often happens like when a car runs up underneath a big truck. Very inconvenient for the occupants of the car if they don't get their heads down. And it's a really nasty collision. But, you know, that can happen, right? Okay? Or cars can otherwise even head on, lock their bumpers or whatever, okay? Intertangle their engines. It's not funny because that's usually a pretty bad car to be in. Anyhow, if the objects merge, then we say that the collision is perfectly inelastic, okay? And it turns out, and we'll prove it later, that in a perfectly inelastic collision, you minimize the kinetic energy afterwards. Okay? Now, the mathematics of these types of collisions is actually pretty simple, especially the inelastic collisions, as we'll see shortly. Okay? Excuse me. In any collision of two objects, the two exert equal and opposite forces on one another. How could I possibly say that? Well, the forces are Newton's third law of pairs. They're equal and opposite forces, okay? One fist, that the fist exerts an equal and opposite force on the hand, right? Okay? And of course, it's not a constant force in that case, but whatever it is, okay, if two objects, there's a plural there, if two objects are isolated from other forces other than the force of interaction, then the impulse momentum theorem holds. It's just an analog, but a different theorem of the work energy theorem. And when we first talked about how you get the work energy theorem for uniformly accelerated motion, in other words, for constant forces, we just plugged F over m into one of the equations of uniformly accelerated motion, and we got the definition of work and the definition of kinetic energy, which, since it's one of the problems that might well occur on your major quiz, you better know. Okay? Then, little side note here, right in a different color. Using this equation of motion, okay, you get, and actually, and I've been using V sub I for initial because V sub 0 is often taken to mean the velocity at time t equals 0. Okay, even if the thing wasn't even moving at time t equals 0, in which case it wouldn't be worth much. Okay, anyhow, you take this equation, very simple equation, right? Just a definition of average velocity, right? And you replace A with F over M, and you do a couple of very simple steps, you get F delta T equals, this should be a VI here, MVF minus MVI, which is the change in MV. Now it is possible that over a time interval, both the force and the mass could change, or one or the other. Okay, in a rocket, over any time interval, if it's burning fuel, it's going to reduce its mass, right? In which case, we got to use differentials. We also have to use differentials in doing error analysis if we're going to do it rigorously, okay? Neither of those things is on the major quiz this week, okay? But both of them will probably be on the midterm in a couple of weeks. So you want to kind of make note of it. Now, do we see the principles behind this? What are the principles? Jot it down. I'm not going to look, but just go ahead and jot down the principles that we've applied here.